Imagine trying to trap a star inside a machine you could walk around. It sounds like science fiction, yet it is the dream behind fusion energy. A dream shaped by decades of belief that only massive machines could ever make it real. Projects rose on this idea, growing larger, heavier, and more complex as scientists chased a reaction that powers the sun. But then a small team dared to ask another question. What if size was never the key? What if a compact reactor built with new materials and faster methods could outperform giants? That bold shift sparked a new chapter in fusion research. Why size once ruled fusion research? Fusion appears easy to describe. Take two atoms of hydrogen, force them together, and they release energy. This is what the sun does every second. But the sun can do this because it is unimaginably massive. Its gravity holds atoms so tightly that fusion happens naturally. On Earth, we do not have this luxury. To reach similar conditions, we heat hydrogen to temperatures around 100 million C. At these temperatures, hydrogen becomes plasma, a swirling state of matter that behaves like both gas and electricity. Plasma cannot touch metal because it would melt anything instantly. So scientists learned to suspend it with magnetic fields. These magnetic fields shape and hold the plasma to float. Early fusion experts realized that larger reactors held plasma more effectively. Bigger machines meant longer confinement and better stability. This belief influenced every major fusion project, especially ITER, the giant TOKAC built in France. ITER became the symbol of scale-based fusion design, rising as a global effort with 35 nations supporting it. The math behind fusion also encouraged going big. According to the Lorson criterion, fusion requires the right balance of temperature, density, and time. If confinement time is short, the other factors must increase dramatically. That pushed engineers toward massive machines with huge plasma volumes. But the drawback was clear. As reactors grew, their timeline stretched, costs exploded. The dream is stuck in delays and revisions. Fusion was always called 30 years away, no matter the decade. Even with world cooperation and record budgets, progress seemed trapped behind the size of the machines themselves. The magnet breakthrough that changed the field. Then, something shifted. Some researchers started asking another question. Instead of building bigger machines, could we build stronger magnets? That idea rose from new superconducting materials known as REBCO tape. These materials can carry enormous electrical currents without resistance, and can do so at higher temperatures than older superconductors. Traditional magnets used in fusion reactors must stay extremely cold, close to absolute zero. And even then, they struggle to exceed magnetic fields of around 12 Tesla. REBCO coils can surpass 20 Tesla. In fusion physics, a stronger magnetic field does not simply improve performance a little, it transforms the entire system. Confinement scales rapidly with magnetic strength. A reactor with double the magnetic field can become many times more efficient because the plasma behaves more predictably and remains stable longer. This meant a smaller machine could suddenly compete with or even outperform a larger one. MIT and Commonwealth Fusion Systems recognized this opportunity and designed Spark, a compact tokamak using these powerful magnets. In 2021, they tested a full-scale magnet coil. Engineers carefully increased the current, watching for any sign of instability. When the coil reached 20 Tesla without quenching, the room erupted. It was not just a successful test, it was proof of a new path. The achievement attracted huge investment, more than $1 billion in months. Critics who doubted small reactors admitted the result was real. For the first time, there was experimental evidence that compact high-field reactors could challenge the belief that fusion must be gigantic, slow, and endlessly expensive. It marked a turning point, showing that innovation in materials might speed fusion progress faster than scale ever could. Spark, the machine built to change the rules. Spark, short for smallest possible, affordable, robust, compact, represents a new philosophy in fusion engineering. Rather than attempting to build the perfect machine all at once, Spark focuses on building the smallest machine that can reach net energy. Its chamber is only about 3 meters tall, tiny compared to it. Yet, it will generate magnetic fields twice as strong. 18 REBCO-based superconducting coils will create a field powerful enough to squeeze plasma at pressures far greater than anything seen in past compact reactors. Spark aims for a fusion gain of 10, meaning it hopes to produce 10 times more power than it uses to heat the plasma. Such a breakthrough would arrive well before ITER, which does not expect similar results until the 2030 SP Spark is not meant to be a power plant. It is a demonstration machine. Its purpose is to show that compact high-field fusion is possible. Once that is proven, the team will build a larger but still modest reactor designed to deliver hundreds of megawatts of electricity to the grid. This two-step plan avoids placing all bets on one enormous machine. It allows fast iteration, quicker feedback, and reduced risk. Construction of Spark began in Massachusetts in 2023. The plan calls for first plasma in 2026, followed by tests that might achieve net energy shortly after. Compared to the $50 billion scale of ITER, Spark's roughly $3 billion cost feels almost small, especially considering it is funded largely by private investment. Its design also includes modular magnets that can be removed or replaced without tearing apart the entire reactor. Its cooling systems operate at higher temperatures than older superconductors, simplifying engineering. Even the structure is lighter and more flexible, potentially allowing future reactors to be built much faster. Spark represents not just a machine, but a shift in how fusion might be developed: smaller, smarter, and more adaptable. The difficult problems still standing in the way. Yet Spark faces real challenges, and none of them are small. A compact reactor means tight margins. Plasma at 100 million is difficult enough to control in a large machine. In a smaller one, even tiny disturbances can cause the system to shut down. Control systems must react faster than any human could notice. They must catch problems in microsecond seconds to keep the plasma stable. The magnets, while powerful, have never been used inside a full fusion environment before. Fusion reactions release high-energy neutrons that strike materials with intense force. Over time, these neutrons damage metals, insulators, and superconducting layers. No one knows exactly how long REBCO coils will survive under this stress. If they degrade faster than expected, the machine could need constant repairs. Heat exhaust is another major challenge. Fusion reactions produce extreme, localized heat. Parts of the machine, especially the diverter, experience temperatures higher than those inside rocket engines. Larger reactors already struggle to handle this. Spark's smaller scale makes the challenge even harder because heat builds up faster and has less room to spread. Engineers are studying tungsten tiles, liquid metal surfaces, and advanced cooling systems. But none are fully proven at Spark's expected power density. Fuel supply adds another layer of complexity. The deuterium-tritium mixture used in Spark requires tritium, a rare and radioactive material. The world's supply is only a few. Future reactors must learn to breed tritium inside the machine, but this technology is still being refined. Spark must also navigate new regulatory territory, since no private fusion machine has ever produced significant energy. All of these challenges create uncertainty. Yet, there are also necessary steps toward building practical fusion power. Why Spark matters, even if it fails. Despite all these obstacles, Spark does not need perfect success to influence the future of fusion. Even if it fails to reach a gain of 1, it will produce data that the world has never seen. It will reveal exactly how high-field magnets behave in a real fusion environment. It will show how plasma reacts inside a compact tokamak. It will expose weaknesses in materials and designs, allowing future machines to improve. Fusion has always moved slowly, sometimes painfully slowly. Many snorts of the people working on Spark have spent their careers inside projects that were delayed or redesigned again and again. They know the risks. They know this machine might not work as expected. Yet they continue because the potential is too important to ignore. Spark represents a bold test of an idea that could reshape an entire field. It shows that innovation does not always require massive budgets or enormous facilities. Sometimes it requires a small team, a new material, and the willingness to challenge decades of assumptions. Even if Spark falls short, it will push fusion science forward by showing what works, what fails, and what comes next. Every piece of progress, every measurement, every lesson will help build the reactors of the future. It is a reminder that scientific breakthroughs rarely appear in perfect form. They emerge through persistence, determination, and countless attempts that pave the way for success. If Spark reaches its goals, it could mark the moment fusion shifts from a distant dream to a technology ready for real development. If it struggles, the knowledge gained will still guide the next machines, including ARC and the reactors that follow. Either outcome moves fusion forward. A small reactor with bold design choices is now competing with giants, proving that progress does not always depend on size. It depends on creativity, courage, and willingness to try new things. Spark is more than a project. It is a sign that the path to fusion may be closer, faster, and brighter than anyone expected. Thank you so much for watching all the way to the end. If you enjoyed this deep dive, please smash that like button, share your thoughts in the comments below, and don't forget to subscribe and turn on notifications so you'll never miss a future update. We've got a lot more exciting tech stories coming your way. Until next time, stay curious, stay inspired, and we'll see you in the next video.